Hello, everybody. When we are talking about carbohydrates, one of the very defining features of carbohydrates is that they can have chirality, or they usually have chirality, which makes them quite interesting molecules. So, what does chirality actually mean? Chirality is a property of a molecule that makes it non-superimposable on its mirror image. And as you know, everything has a mirror image, apart from vampires. They don't have mirror images, but we don't deal with vampires here. And these mirror images very often are not superimposable. We can't put one side of the mirror on top of the other side of the mirror. So when you, for example, look at your hands are mirror images of each other, so the left and the right hand, and you can't superimpose them so that they are exactly the same. That's why we have a left and a right glove, for example. And a chirality actually means literally handiness. So, what is important for chirality? In terms of chirality, we need to recognize that this is a feature very often of carbon. So, I've drawn here a carbon molecule, and chirality in carbon can only happen when this carbon is sp3 hybridized. We cannot have a chiral carbon that is only sp2 or sp hybridized. And then we have four different connections of this carbon in the middle. It is four different bonds, different groups, and a chiral molecule has at least one of these asymmetric carbon atoms. So we can look at this molecule, for example, and say the mirror image that we get here. So here would be our mirror, and we can form the mirror image, but we can't put them really on top of each other. Don't forget, when we draw it like that, these bonds here would sort of stick out of the plane, and we can't superimpose them. These mirror images are called enantiomers. There's this specific term, which means they are two mirror images. And achiral molecules, which don't have these chiral center, can be superimposed on the mirror images because they've got an internal symmetry. So when we, for example, look at a glucose molecule, we see that, so here this would be glucose molecules, and we here have the aldehyde. Here we've got the body of the glucose molecule, and what we can do is we can sort of do a mirror image of these glucose. And what we see is the aldehyde. This is, of course, sp2 hybridized. sp2 hybridized. All the others are sp3 hybridized. And we can now check what actually how many chiral carbon atoms we have. We can look at these carbon atoms and say, so this one here is definitely not, the first one is not a chiral molecule. Now, is the second one a chiral molecule? Well, it is connected to an H, an OH, an aldehyde and the rest of the molecule. So we definitely can say, yes, this molecule is chiral. Now, what about this molecule here, the next carbon here? We see it is connected to an OH, an H. Then it is connected to this molecule, part of the molecule, and this molecule. So it's also a chiral molecule or carbon. Likewise, this one and this one. What about the last one? Let's have a look at that. It is connected to an OH, but it's connected to two H, so they are the same. So this one here would not be a chiral atom in this glucose molecule. So we've got 1, 2, 3, 4 chiral atoms in carbon atoms in glucose. And when we look at the structure of the enantiomer, so they are enantiomers, and we see we've got here the mirror image, but we cannot superimpose them onto each other. So here we've got these enantiomers of glucose with 4 chiral atoms that we have here in the structure. And important, it must be sp3 hybridized, because only then it has no internal symmetry. And this structure here is absolutely essential for the biological function. So, for example, we can nicely use this particular glucose, but this type of glucose is not usable for biological systems. Not used by biological systems. Or very, very rarely. So this is how chirality actually plays an important role in the structure and the function of carbohydrates.